Take a look at this small, unassuming piece of plastic and metal. It might not look like much, but this tiny component has completely transformed how we live. Without it, we wouldn't have the compact smartphones in our pockets or the powerful computers we rely on every single day. This is a bipolar junction transistor. In simple terms, it acts as a brain that controls the flow of electrical current in a circuit. Today, we are going to dive deep into the specific mechanics of the NPN type transistor, exploring its physical reality, how it effortlessly controls massive currents, and the industry's secrets to keeping it stable. Let's look inside. An NPN transistor is essentially a microscopic sandwich. It consists of three distinct layers of semiconductor material: the emitter, the base, and the collector. But they are not created equal. The emitter is heavily doped. Its sole job is to act as a massive reservoir, providing a huge number of electrons. In the middle, we have the base. The base is extremely thin and very lightly doped. Think of it as a highly sensitive control gate. Finally, we have the collector. It is moderately doped and physically the largest of the three parts, specifically designed to collect those electrons and safely dissipate the heat generated by the process. So, how do these three parts interact? The entire magic of the transistor relies on one key concept: using a very small input to control a much larger output. When we apply a small voltage to the base emitter junction, we forward bias it. This acts like opening a valve. Electrons rush from the emitter into the base. But because the base is so incredibly thin and lightly doped, there isn't much room for them to stay. As a result, about 95 to 99% of these electrons shoot straight through the base and are swept up by the collector. This means a tiny base current creates a massive collector current. In engineering, we define this relationship with a simple formula: IC equals beta times IB, where beta is the current gain of the transistor. Understanding how current flows is only half the battle. If we want to use this transistor in the real world, say as a linear amplifier, we need to control its operating state. This is called biasing. Our goal is to establish a rock-solid Q point or quiescent point. If the Q point shifts due to heat, our signal gets distorted and the transistor could even destroy itself through thermal runaway. So, how do engineers solve this? They use the voltage divider bias. Look at this circuit configuration. By using a network of resistors, the voltage divider bias provides a fixed base voltage. Why is this the best choice? First, high stability. It keeps the Q point locked in place even when the temperature in the room changes. Second, it provides beta independence. If a transistor breaks and we replace it with one that has a slightly different gain, this circuit design ensures the overall performance is not affected. It is predictable, it is reliable, and that is exactly why this method is the industry standard for circuit designers worldwide. In summary, the NPN bipolar junction transistor is a fundamental building block of modern technology. By utilizing a microscopic, lightly doped base layer, we can control large currents with incredible precision. And by applying professional biasing techniques like the voltage divider bias, we ensure those circuits run flawlessly, no matter the environment. Thank you for your attention.